Okay, so we will begin. If other folks do join, that'll be nice. If not, I'm sure they can watch it later on, and I will definitely upload this as soon as I get the recording back. Um, you know, this is the first lecture, so I definitely want to take time to give you an overview of what this course would be like. And more importantly, deep learning is a kind of a subject that is a very advanced subject because it builds on a lot of other stuff. So it's very important to like have at least some understanding of what it builds on top of, and you will see later on. And I don't know if you saw the modules, but I have definitely highlighted that linear algebra and machine learning is like very important to understand deep learning. Today we'll try to wrap some of the fundamentals, and hopefully this is not something new to either of you. I'm really hoping that you guys already have some understanding of basic discrete math, some understanding of machine learning, and if not, I will definitely provide you some materials that will allow you to get up to the speed. But having done some machine learning course is definitely a good place to be if you are trying to learn the deep learning. uh, you know, I know it's only three of us, but we can at least take time and introduce ourselves, and maybe other people who will watch it this later on. They can use the discussion forum on Canvas or the Slack channel that we have to introduce themselves. I am Adi Prakash. I work as a machine learning scientist at a drug discovery company. We are trying to find drugs for aging, and you can see how like trying to tell whether or not a drug will work for a certain disease. It's kind of a data-driven problem, right? You have plenty of potential candidates, and then you want to also see how effective they will be, right? Because we like to think drugs in terms of binary. That is, will it work or will it not work? But often it turns out that there is this uh, there is this how well does it work, how quickly does it work, because there are a lot of drugs that work, but the rate at which drugs cure the disease is slower than the rate at which the disease spreads, so that drug is of no good, right? And then also it turns out that different people react differently to some of these drugs, especially the new type of drugs. These are called as immunotherapy drugs. And before this drug discovery company, I was at AI for pathology company, where we try to do cancer diagnosis, where we try to detect cancers in patients as soon as possible. Because oftentimes, in the case of cancer, if we detect them soon, it's easy to find a cure, easy to fix the problem. But if you find it too late, there's not much you can do, because there aren't that many drugs for cancer. So I worked there for almost 4 years. Before that, I was at another, like Philips Research. That's a big company where, again, I was trying to apply AI to basically catch if there is some kind of a misdiagnosis, because oftentimes doctors will, because they're only seeing few data points, and sometimes they don't get the holistic overview, and there are a lot of cases of misdiagnosis, and a lot of people do die every year because of their either correct disease was not caught, or they were given drugs for the wrong disease, and therefore that leads to complications and even death. And my goal was, can we use AI to basically try to catch these things before it's too late? I know these things are all work in progress. If you don't see them at your doctor's place right now, is because there's a regulatory approval process that has to go through, and machine learning is a new space. Therefore there is a more scrutiny, because the way humans can be wrong, even machines can be wrong, even the AI can be wrong. So that's why if you don't see them, that's the case. So so Tim, Stefan, do you guys want to take maybe a minute or two and introduce yourself, what you do? But if you don't want to, that's fine by me also.
Sure. Yeah, I can go ahead. I posted in the discussion, but I have a bachelor's in electrical engineering, but I've been working for Verizon for a little over 10 years now, working in the radio access network. So basically building out the cellular industry in New England. About 5 years ago or so, I moved into the headquarters group and started working on automation algorithms, because we can't keep up with technology, and we just need to supplement with some automation and scripting. So did that for a while, launched a centralized platform to do some automation at scale on the cellular network. And then for the last almost year now, I've moved over to a planning and technology group that focuses on AI and ML, trying to get some on-the-job training as I'm transitioning to a data science role. So have a little bit of experience so far with a couple different problems in practice. There's a lot of stuff to try to predict in the telecommunication space, specifically around network performance, not about like finances or customer satisfaction, but I try to focus on, predicting root cause analysis, some of the optimal settings that we could use, simulations, and recently working with one of the data scientists, she was applying convolutional neural networks, and I know very, very little about them, just high level. So I'm hoping to get a little bit deeper understanding about some of the more advanced algorithms out of this course.
Yeah, and we will definitely study a lot about convolutional neural networks, because that is like the essence, the central block for most of the modern deep learning. And most of my PhD, which was a while ago, also focused on convolutional networks. Yeah, thank you for the introduction. That was interesting. Stefan, do you want to go?
Oh, yes, absolutely. So yeah, my name is Stephen Bodie. Originally, I'm from Ghana. I live in Worcester, Massachusetts. And I do currently work as a data analyst for Polar Beverages. Polar Beverage, I believe most of you, if you live in Massachusetts, perhaps is one of the largest independent bottling company. So we are into the production of salsa. If you're a salsa fan, hopefully you may probably come across our brand. So I had my undergraduate degree in mathematics and statistics. Professionally, I don't really have a lot of coding or programming experience. Back in my home country, we did more theoretical stuff. So I'm trying to do a little bit of coding, the R, the Python and stuff. So I've taken a few courses here and there. I'm still not there as I wanted, but hopefully I took the machine learning 1 and 2. That got me really comfortable. So I'm hoping that deep learning would also take me to a different level. But yes, I'm looking forward to enjoying this class, and hopefully I would be able to explore as much as I can as far as machine learning. Over the past, I've developed a very strong interest in AI, and hopefully at some point I might want to pursue further after this program.
Perfect. So the ML 1 and 2 course you took didn't involve any programming or coding exercises?
Oh yes, we did. Of course, we did a bunch of Python. Actually, we touched a little bit on the Keras and TensorFlows, stuff like that. So, like I said, I'm not just that I'm still not too comfortable. So,
no problem. Stephen, have you joined the Slack channel?
Was that?
So I have set up a Slack workspace.
Yes.
So, like if you have any questions regarding Python or coding, feel free to post there anytime. And, if I have time or if other people are there, they might help you. Yeah.
Thank you very much.
Okay. So, the logistics is, I think, very important, because ultimately, my goal is definitely that, at the end of the course, you guys come out where you feel confident that, you can not only understand the underpinnings of this stuff, but also develop this stuff, right? Because, it's very easy to simply watch, a set of videos on YouTube and, say, oh, I understand deep learning. But the difference between that and taking actual course is course will make you do the work, right? Because and only when you do the work, then you will really understand. Because and trust me, that I have seen so many people I've taught, and I've given random lectures, random seminars, but I've also taught in a course setting. And if you don't take active approach to learning, you'll only be you don't understand these things from 10-foot pole. You won't really get to know how they work. And if you want to get a job where this is your full-time job, being able to do that part is very critical. So you'll see that project and assignment are where all your grades will be. Class participation is 10% that we can decide how we will do it. Either if you're coming to the live lectures or participating in Slack. But as you can see, there are no quizzes, no final, because if I simply ask you some theoretical, like, oh, which of this is the right answer to X, probably you will get that even if you don't really understand how X works. But being able to do some assignment and get some results, because machine learning is all about getting some results that somehow seems magical. And therefore I personally feel that the right way to test is to see your involvement in assignment projects. And this is like, I will be there to help you. And I realize that not everybody might have same the programming. So if two people want to get together to do a project, I will consider that only if your strengths are complementary. That is, one person has good mathematics background, other one is good at programming. If you come together, but if you have very similar backgrounds, probably you will get best by doing the project on your own. But if you have to combine with somebody else, up to another person, I will allow that. As far as the reading material goes, I'm sure you guys have seen, I have listed 2 books. The first one, the reason I made the first book as like the actual course book, and of course you don't have to buy this book, like all this material that I'll provide will be sufficient and will not rely on the book. But there are chapters on the book that will be like part of the lectures, and therefore if you read the book as you go and if you try to do this stuff, I think you will get along well. And plus, you'll be reading book along with other people, and therefore, you guys can also help each other out. I'll also be there. And therefore, this is, if you're waiting for a time to read a book cover to cover, I would say now is the time, because after the course has ended, even if you do pick up a book, you will not get as much out of it as you would get now. So I recommend the first one. Second one is actually my favorite book. To be honest, in other parts, in other places, when I teach deep learning, I actually refer to this book, but that is like more theory and more involved. And that is where a semester is almost 4 months long. This is too dense a book to really finish in 2 months. So I would not recommend this as a main book, but you should definitely read some of the chapters of this. It's first few chapters are easy to digest, and this book will really give you more of the background, more of the theory than the first one. But first one will really give you the practical aspects with the actual piece of code. And the guy who wrote this book, Francois, he's also the developer of Keras, and Keras is one of the libraries we'll be using in this course. So you can see how he's the best person to teach you how to use Keras for some of this stuff. So I hope you will try to read the book chapters as we cover them, and feel free to ask anything to me or other students in this class. And like I said, the project, maybe individual, but I'll allow you if you want to combine with another person. So the way we will submit project in this is either you will submit a Jupyter notebook, and if you have no idea what that is, I will show you later on today, or you will submit a Colab notebook, which is just a Jupyter notebook, that is hosted online, and it is sponsored, and it is free to use, and it is supported by Google. And the reason I encourage Colab notebook is, typically when you run Jupyter notebook, you'll be running on your computer, and probably you have a laptop or something. You might not have a GPU, but Colab notebook, you can freely use a GPU provided by Google. And in deep learning, the reason deep learning really took off in 2012, and you will hear more details about this from me in the coming weeks. If you had to ask me, and if you have to ask, even other big people in this field, like even like Andrew Ng, who's a Stanford professor, who's credited for the success of the deep learning, even he agrees that it was actually not the data, not the algorithms, but ability to use GPUs to basically do these heavy computations that led to the growth of deep learning, because deep learning really requires a lot of compute, and you cannot scale that kind of computation on CPU because you can only have so many cores. But in GPUs, you have a lot of small cores, and therefore you can easily parallelize your computation. And therefore, running same thing, some of the assignments which I will give you, if you run them on your own laptop, I will try to keep the assignments light enough that you could run in your desktop or laptop even without GPU in a couple hours, but you could easily run them on Colab, where you get a free GPU and run them in a few minutes. And it's that much of a difference, few minutes versus like half a day. So that's why I encourage you, and I will show you later on today how to use Colab and how to get a free GPU. And like when you're getting a free GPU, you can't run something for like 1 week. After one day, they'll kick you out. But to be honest, my experience has been that for a couple of days, they don't kick you out unless they need the GPU. So I will show you that. Hi, Durga Rao. Welcome to the class.
Yeah, hi class. Hi professor, thank you so much.
No problem. Yeah. So, just a while ago, we all went around and introduced ourselves. You kind of missed the part where I, Tim, and Stephen introduced ourselves. But if you do watch the video later on, probably you will get, you can hear about that. But do you want to take 2 minutes and introduce yourself, what you do, and, why, what interests you to this course?
Yeah, hi professor and class. My name is Durga Rayapudi, so people can call me Durga. I am from India, but I have been living in States since 2010. So it's almost, I completed 12 years, and 2011. So almost 10 years I completed. Right now I work for Verizon as a software engineer in Walnut Creek. So I'm California based. So I'm in PST time zone. So like I will be like swapping between my office laptop and personal laptop based on that's the reason I was late. And I'm a Java developer. I have been a Java developer from the beginning of my career in software development. So I joined masters in data science. I wanted to shift to data science world. That is my initial goal. But due to personal commitments and other commitments at work, I'm not like a so active participation in taking the courses. I'm taking a lot of gap between each course between the classes. I mean to say that I took a while ago ML1 and ML2, machine learning 1 and machine learning 2 a while ago. And those two classes were taught in programming language R. Though in spite of like I requested those professors like teachers in a Python programming language, because at our work and in other places, I see that 80% of the people at least prefer to use Python or R, especially when it comes to data science or ML. Maybe I'm wrong, but I see that based on personal experience. So with that said, I have a zero experience in Python. And at the same time, like I have some kind of an experience with ML1 and ML2, but I need to have a refresh. I need to complete. I forgot like what I studied. So that's all about me. Thank you, professor.
Yeah, no problem. So Durga, you and Stephen, you both are, I think, the same place where maybe, you might need a refresher on Python. So what I'll do is after the class, on the Slack channel, I'll post, and maybe we can figure out a time where, or maybe this week's office hour, I'm happy to, do a hands-on, quick refresher on Python. Trust me, it's the easiest language to learn. And if you already know a programming language, it's really a matter of one day where you just connect the dots and you're like, oh, instead of this, I use that. And hopefully, a week or so this week's office hour, I can help you guys, come up to the speed on Python.
And me and Tim are classmates in my very first course, and me and Stephen are classmates in my previous classes. So
yes, absolutely. I am very familiar with you, Durga. We've been in classes, so we know each other. Yeah.
Yeah.
And so as far as this course goes, if you want to do your assignment in R or Java, I will be totally fine with it. But if your goal is to get into data science, you should definitely use Python because it's not 80%. I'm confident in saying that more than 95% of data science happens in Python. Well, because people will often say, oh, Python is not fast, right? It is supposed to be easy to learn, but it's a slow language. But the thing is, Python is only used as an interface. It's an API because underneath all of these code, they run on CUDA, and CUDA is a language for the GPUs. It's like a C-type language, but designed by NVIDIA. So it doesn't matter whether you use Python or R or Java, at the end, all of those code will get converted to CUDA and they'll run at the same speed. And that is why, if they are all going to be the same speed, you might as well use the language that is most easy to learn, easy and most convenient, right? In fact, like a few years ago, so there are two most popular libraries for deep learning, right? One is called as PyTorch from Facebook, and one is called TensorFlow or Keras from Google. And a few years ago, actually, PyTorch was called Torch because it was in language Lua. And they realized the only reason it wasn't getting as popular is because more people were familiar with Python. So Torch people decided to rewrite Torch and make it, make Python as a front end, the front API, and now it is more popular than TensorFlow. And Keras is more like in the middle, where Keras is a higher level language built on top of TensorFlow. So I would encourage you to, try to learn Python. At least this will help you in the long run to stay in data science. But if you're like, oh, I'm already doing a lot of stuff, I don't have time to learn Python.
Definitely, Professor. That is
Yeah.
one of my goal actually. I wanna make myself comfortable with the Python programming language. So that is my goal, one of the goal for this class.
Okay. And I'm happy to help you learn. If you have questions, you can always ask on the Slack channel.
Yeah, sure, Professor. Sorry for cutting you.
No,
I have
no,
a question. I thought TensorFlow, you're mentioning TensorFlow and Keras. In ML2 machine learning 2 I think assignments, I think we were using a couple of weeks TensorFlow. I think R integrated TensorFlow. We try to actually accomplish some of the assignments in TensorFlow. I still remember Keras and TensorFlow. Does it mean that TensorFlow is a separate programming language from Python, or it's a part of the Python, a library in Python?
Yeah, it's just a library. TensorFlow is a library where you can write in Python programming language. And when you call the functions in the TensorFlow, in the backend, it will convert your Python program to the relevant CUDA program, and then it will directly talk to the GPU. So TensorFlow is your interface to running on GPUs. But the problem is TensorFlow is a slightly lower level API, and therefore we'll use Keras, where, because there's a lot of boilerplate code you'll have to write in deep learning, and therefore Keras provides a higher level abstraction, so that, if you want to use convolution, you can just write one function for convolution and do the convolution. You don't have to actually write all the matrix multiplication and those stuff. So if you are a learner, best to stick with Keras, because all the low level problems and those things abstracted away. But if you are like advanced learner, probably you should try to write low level stuff in TensorFlow or PyTorch. Does that answer your question?
Yes, Professor. Thank you so much.
Okay. Okay. So this is what hopefully we will hopefully we'll have time to cover all of this. The very first question is, as some of you have already taken some machine learning or already have idea of what machine learning is, and this course is called deep learning, the obvious question comes, like, why a separate course on deep learning, right? Why is it not just ML3, right? Why call it a different name, right? And again, this is very popular in deep learning culture to use a lot of memes. And here, just one of the meme. And if you don't understand some of the words here, not well explained, but this is the kind of the idea where, machine learning is a really old field, and for a long time, like for 4 or 5 decades, the improvements were like marginal, right? If you had, so people initially started with these linear models, and linear models means you just try to find one line that separates your data points. And then if you do that, and suddenly when you have outliers, like suddenly when the house prices during COVID went so high, these linear models that predicted house prices started failing, right? Because if you had a model which said, oh, let me take the number of bedrooms, the square footage, the location, multiply each of them by some number, and if I add them, and that is my house price, that kind of model works 80% of the time, but then fails when you have outlier data. And then, then you have other techniques that will handle outlier data, like, other non-linear machine learning type models. But then what happens when someone with the features are highly correlated? And then ultimately you realize the only way to really learn from the data is to give up on the linearity. Linearity means like simple association, right? In our head, we also try to think of it as like distant trees, right? Okay, do you want, so let's say, what movie do you want to watch? So you'll ask yourself, okay, maybe do you want action, or do you want a comedy? So you will say, I want a comedy. Do you want the movie to be longer than 2 hours or shorter than 2 hours? So in this way, when you make all these decisions, these are very simple because they're easy to interpret, but then turns out they have limitations on what they can do. The ultimate power of learning comes by adding this non-linearity. Non-linearity means the association between input and output is not so simple to see how that relationship came about to be. And therefore, non-linearity is considered like a superior way of mapping the data. And deep learning is all about adding non-linearity. That is, when you go from data and then many layers of non-linearity, that is, you take a data, do some non-linear transformation to some other domain, then do another non-linear transformation to some other domain, And again, if these words are not familiar, hopefully the refresher will help you. But idea is you keep applying these nonlinearities so that data becomes so easy to then do a classification of. So this is just one of the mean. But this is a more serious, very high level idea on why deep learning is different than other types of machine learning, right? In all the other type of machine learning, whether it is rule-based, like I said, some kind of decision tree, or some, classical machine learning where we have these features, in all of them, you have to design these features. You have to say what is important to me in order to do this task. Nobody's gonna give that to you, right? And there's no harm in that, right? Because if you're trying to, predict, let's say, weather forecast for tomorrow, right? So you will say, okay, maybe the wind speed is important, maybe the humidity is important. So these are the features. But there are only so many features that you can think of, and oftentimes features correlate themselves, and therefore what you can learn is very limited. In deep learning, the big change that comes is you try to give the rawest form of data to your learning, that you say, I don't know any feature. I don't want to design any feature. I just want to throw all data points that I have. And then I'm hoping that my system will learn the features itself. And the system will basically be, several layers of this, learning features over features over features, and then you get the output. And this is what is called as deep learning, where initially the data is as raw as possible. So, in case of images, every single pixel. In case of sound, every single wave, right? In case of video, every single frame. In that way, you don't tell where the object is in the video. You just say, take all the data that I have and now learn. And as you can see, when you do this kind of thing, the amount of data that you're giving to the model blows up by significant, orders of magnitude, by orders of magnitude. And that is where some of the innovations came about, because for a long time, people in machine learning believed that you know what, you need to you cannot have too many you can't have too small a signal to noise ratio. That is, you need to have some amount of representation of what is useful and what is not useful. Because if I give you 1,000 by 1,000 images of a cat, right, in that 1,000 by 1,000 images, probably the pixels that represent the cat are going to be 20% or less. In fact, sometimes even 2%. It means 98% of the data they're giving is not useful. And typical, machine learning models, what we call these days classical machine learning models, fail because they cannot operate on such a low signal to noise ratio models. But in deep learning, these models are designed to take such a low signal to noise ratio models and then keep amplifying the signal and reducing the noise. And that's the key difference. So that comes. I will, quickly go over this, history of deep learning, just because, if I take on a course, people might want to ask, although, and I asked this professor and he said I could use his slides so that I don't have to, recreate the same set of slides. But to be honest, I will try to just skim over this. You guys, there's a corresponding video of this lecture. I'll put a link to that video so that you can watch that video if you want to learn in detail how we got here. But just to give you some idea, because maybe these things will also shape your understanding of why we are studying these things, right? Because you will see that in most of the course we will study things related to computer vision, and we will study things related to neurons, like neural network, and you will study things related to convolution. And we'll say, why did we decide to do these things? This seems so arbitrary. But it turns out they are not arbitrary, because there is some inspiration, right? So one of the words you will hear in textbooks is called as Hubble and Wiesel model for human vision, where these two folks, I don't know in which year they did this experiment, where, and they won Nobel Prize for it, where what they did was they tried to show different images to cat, and then they had these raw probes in the cat's brain and tried to collect what kind of output you get. And very quickly they found, and this is very important, right? Because very quickly they found that the brain cells, the visual cortex related neuron cells, they respond to a certain type of shapes. That is, they respond to edges, but not just edges, but they also respond to the orientation of edges, right? So therefore, if this line had a different orientation, the firing of neurons will be different. And eventually they also realized that so this kind of pattern matching happens, and eventually, how does a cat know if something is an object is by combining the signals from all these very primitive, let's call them recognizers, right? Where, oh, there is a line of this angle, there's a line of that angle, and when these two come together, they form something. And the reason I'm saying this is because that was an inspiration for artificial neural networks. That is where you will see, even in the convolutional neural network, for which we'll spend a whole week, they really try to, and this actually happened by chance, that when people build convolutional neural networks, they found that even convolutional neural networks try to learn different edges, edges of different orientations and different, color shades, less about the specific objects. Their goal is, let's try to take primitive shapes, call as motifs, and then combine it to form what are known shapes. And surprisingly, how artificial neural network works and how brain works are very similar in that regard, although it is purely by chance. That was not the intention. And therefore, that people think that the reason deep learning is so successful is because it is mimicking human intelligence, which again, GEO isn't out yet, and I have spent many years in this field, and you will see every other year people will try to disprove the existing techniques. So let's just, they are very similar, but I don't want to say that is the only reason it's so successful. And I think back in the 60s, there was this big summer project at MIT where they wanted to see if they could build an artificial intelligence system. And this was even before we had modern computers. And I think this is traced back as the source of the start of the whole AI and deep learning. And now I'm sure you guys are familiar. It is used in every domain, everywhere. And computer vision is really key. In fact, even in things like languages, the techniques that came out of computer vision are the most successful ones, and you will see towards the end of the course, I will give you some examples of those. And so this is a now difference between what did we do for computer vision before deep learning came and what are we doing now, right? Like I said earlier, before you had to have this idea of features. Now, if you're trying to predict house prices, you know what features to use. But if your data are images, and if you have to write features, then these features were called as SIFT, hard. These are all basically your some kind of frequency domain transformations, or histogram of gradients. All these are some kind of signal processing techniques, and then people try to apply it on top of images, get something that is smaller in dimensions, smaller representation, and treated those as features, and then try to use classical machine learning models, which you guys are familiar, like SVM, random forest, these things. And this is how people did, before 2012. Now, again, 2012 is not like a 1 year when magic happened. People, you were doing this even after another, but 2012, something significant happened. There was this one, where is this? So there was this one competition, right? And this was running even before. And until 2011, people used to use these, old classical machine learning models on top of these, image-based features. And you can see this is actually error, right? So the lower is better. And you can see error in this level. And 2012, a group of people, including Jeffrey Hinton and Alex Zosky from University of Toronto, they decided to use deep learning. And deep learning was already, it was not invented in 2012, it was already there. There were already papers in 2011, 10, but they decided to use this for this one particular task of recognizing images. It's called as ImageNet Large Scale Visual Recognition Challenge. And you can see they won by a big margin, right? Every other participant that didn't use deep learning had errors around 25, and they were in like 16 or 17. And after that, every subsequent year, it's only deep learning based techniques, and you can see error has gone down significantly. So that is why oftentimes 2012 is considered as the year, everything in deep learning is called either pre-2012 or post-2012, because there was a new enthusiasm around using deep learning for these kind of tasks. And we will of course study in very detail all the stuff that went into this magic box, but you need to know that in 2012 is where things got really popular. And again, this is a full history. If you are interested, watch the video that is part of the slides, and there's talk about AI winter, this, that, but it's not really very important. One thing is important is like these three people who are who independently, like for example Yann LeCun, who gave some of these convolutional neural network related stuff. Jeffrey Hinton, who invented the ways to train these kind of techniques, and Yusuf Benjo, who laid a lot of the foundational work. These three people won a Turing Award in 2019, which is equivalent to your Nobel Prize for computer science. So you can see what the work they have done has really, has been recognized to be, very valuable for the field of computing. And now these are all the conferences where you can see deep learning based papers are just blowing up every year after year. In every other application, people just want to use deep learning, even if the problem seems very, very far away from machine learning or computer science. People use deep learning. People, for example, Google was able to save hundreds of millions of dollars in their electricity bill by optimizing their data centers, and that optimizing process was done by deep learning. So you can see in the things that you not think machine learning would be applied, people have applied it and they have found it useful. And and of course I don't have to give you a tour of the places where it can be used. Tesla self-driving car uses computer vision in their cameras. There is DeepMind has a program called as AlphaGo that won. That's the best Go player. All the translation that happens using this. There are robots that can play games better than humans. There are text generation, all these things. Even your Google Assistant, Siri, Alexa, they are all using deep learning. And this is exactly what I did in my previous job, where these are like your microscope scans of some part of your tissue. And here basically we're trying to tell whether, what parts are cancer, cancer is a tumor and what are not. And sometimes, the AI is able to pick very, very small regions of tumor that every human will definitely, skip over because it's too small for them to notice. But that is the best thing about AI, right? Like every pixel that has same value has equal importance. But for human, like, big things that have bigger value, and that's where AI comes into play. So, I will not bore you with more of the examples. If you're interested, please go through this deck, and there's a video, and you can learn all about, the applications. What we will do is, I think, this is very, sorry, go ahead.
Yeah, I had a quick question. So you've talked a couple of different, I saw like talking about deep learning versus adversarial networks. I think that was the ANDs, right? Is reinforcement learning a form of deep learning, or is that something different?
Yeah, so we will come to that. I do have a slide later on. So
okay, cool. Thank you.
Yeah, so deep learning is just a collection of very specific types of tools used in machine learning, right? And reinforcement learning is just a type of machine learning. Now you can apply deep learning for reinforcement learning, or you can do reinforcement learning using old techniques. And you will see, like everything, even most of the modern reinforcement learning uses deep learning, right? So deep learning just provides you some ways to do different types of learning, and one of the type of learning is reinforcement learning. So all the reinforcement learning agents that play games, they all use deep learning. So yeah, deep learning and not different, just that reinforcement learning is a type of a problem-solving approach, and deep learning is a tool, and therefore oftentimes people will apply them both.
Thanks.
Yeah. Okay. And okay, so how many of you have taken a course on linear algebra, or at least familiar with ideas of matrices, vectors, matrix multiplications, that sort of stuff?
Yeah.
You guys are all familiar with
Yep.
linear algebra? Okay,
Yep.
perfect. I'm so glad. Then I'll just very quickly just run through the slides because I have them, but I will not spend a lot of time here. And then we can take a break, and then we can for 5 minutes and we'll come back again. So and the reason I would mention some of these things is because if you read the textbook, or if you even see the code, all stuff, you will see these things being mentioned, right? So there will be scalars. Scalars are just some single number. It could be floating point, it could be integer, but just single number, right? And these are written always in lowercase and always in italic font. Then of course you have vectors, and we will be dealing with a lot of vectors. And you will see, vector is not really a good term for deep learning, because you will see why. But if you pick up any classical linear algebra book, it will talk a lot about vectors, right? Again, the vector is a collection of numbers. It could represent something meaningful, like directions like XYZ coordinates, or, it could represent steering wheel orientations, but it could also be nothing. And you will see most of the time in deep learning, these numbers mean nothing. They're just a set. They are supposed to represent some idea. And oftentimes, it's a real number. So, and if they are n dimensions, they are written like this, like, X is an element of Rn. Now, matrix is where things get interesting, where now you have these set of numbers, but in two-dimensional axis, right? So you have, so they're represented like this. So they have rows and columns, and you will see, and I will tell you right now, right, that all the problems you will face while doing assignments, while doing projects, will come down to issues with matrices, issues with, matrix multiplications, additions, because ultimately, there are some set of operations that you can do on matrix, but then they need to behave certain, they need to have some properties. And when those properties don't meet, you'll have these errors. And because matrices have two dimensions, they are represented as m cross n, where m is the number of rows, n is the number of columns. Now, but what if there is, instead of two-dimensional array of numbers, I have three-dimensional matrix of numbers, or I have four-dimensional, five-dimensional. So the general term is called as tensors. So whether it is, if tensors are one dimension, so if they're zero dimension, you call them scalars. If they're one dimension, then they are vectors. Two-dimension matrices, and if they are n dimension, is called them n-dimension tensors. They're useful because you will see that very, very often we will be dealing with tensors. They are more than two dimensions, or in fact 3, 4 dimensions, and therefore calling them matrices might just confuse you. So we'll just call them tensors. And therefore, that's why it is TensorFlow, and that's why the hardware is called as tensor processing unit, TPUs. Okay, so because you guys know linear algebra, I will not go over matrix transpose. It's an operation that's highly useful, and you'll see it being done oftentimes. Similarly, matrix multiplication, I'm sure you guys are familiar with dot product that results in a scalar. There's the outer product that results in another matrix. But there is another kind of matrix multiplication that you guys might not be familiar with if you have only taken math. But this is very popular in deep learning. This is the, it has a fancy name called as Hadamard product. But to be honest, it is, it's just point-wise multiplication. That is, if you have two matrices of same size, same shape, each element of that position, you just multiply them. So in this case, 3 is multiplied by 1, 5 is multiplied by 6, 7 with 3. And whatever you get is your resulting matrix. It seems, like there's no much use of this kind of multiplication in linear algebra, in math, in solving linear equations, but it has use in deep learning. You will see, because oftentimes these two might represent different set of signals. Like maybe if you're doing visual question answering, where this represents, a signal from images, this represents signals from your question, and when you multiply them, you have somehow gotten a new set of data that jointly understands images and the text. So this is widely used there. Identity matrix, as you guys know, just once, it's very, very useful, and you will often see this being used a lot of the times, and it's represented by I. Matrix inversion is, again, very important, and you will see I have given a to-do. You can consider that as like, zeroth assignment. It doesn't have any weight to your grade, but I will encourage you to do that to the assignment, because matrix multiplication and matrix inversion are very computationally expensive process. And sometimes by being smart, by figuring out the right way to do matrix multiplication, you can save a lot of computation. And you will see some of the advanced things which we'll study later on. They are designed knowing that there's going to be a lot of matrix computation, a lot of matrix inversion or matrix multiplications, and therefore they're designed in order to make that outcome to be as fast as possible. So some of the decisions are done not because it leads to best result, but it leads to result faster, because it is so expensive. And of course, I'm sure if you know linear algebra, you know that not all matrices can be inverted. But luckily, the libraries which you will use will, warn you if they cannot be inverted. Now, norms is something which, is very, very widely used, because in the end, we will be comparing a lot of stuff, right? We'll be comparing whether, one model is better than another model or not. We'll be comparing whether two data points are same or different. Or we'll be comparing if, their learning is happening at the same rate or not. So whenever you're comparing stuff, you need some kind of a distance or a similarity metric, right? So for matrices, norms, any kind of norm, whether it is a L2 norm, so L2 norm would be just a Euclidean distance, or some other form of norm, is useful because you want to reduce that matrix to some smaller number, or you can compare and get some kind of distance. And again, sometimes you have the triangle inequality. In that case, it is symmetry. It's a metric. Sometimes not. In that case, it is only a similarity. It's only it's not a distance. It's only similarity. It's a measure. But that's a very pedantic difference. You don't really have to worry about that. But you will see. I will show you in the libraries that we'll use. They will have functions to do L2 norm or L0 norm or L infinity norm. You might not get to use all of them, but knowing that all the libraries that you are going to be using have these norms will allow you to will allow you to be in a position where if you need them, you will you know where to find them. Especially L1 and L2 norm, these are like your Manhattan distance or the Euclidean distance. We will be using them a lot throughout this course. So, so this is the computation of your L. So LP norms is just generalization of your L2 norm, where P is just the number, is like this, right? So if P is 2, you can see here, you square all the individual elements and then you sum them and you take square root. And in this way, you get your Euclidean distance. And in L1 norm, you simply take absolute value of all of them, right? And then L infinity norm is very interesting because you take the max. So it's basically you don't care about all the values, you only care about the largest value in the group. And you might say, where is this even going to be useful? And then you will realize that, if especially if you get to like adversarial stuff or trying to find bad examples, outliers, you only care about the worst example. In those cases, it'll be useful. And if you're thinking what these numbers are, they are equation numbers from that book, from where I actually pull this. This is the deep learning book. This is the chapter. So if you go to that chapter, these are the equation numbers, so that if you want to learn more about it, you can follow them there. And of course, about unit vectors, symmetric matrix, and orthogonal matrix. So I won't go into those. Okay, so now that you know this, let's take okay, it's 6:53. Let's take 5-minute break, and let's meet. Okay, it's almost 6:54. Okay, let's meet at 7 p.m. You can take a bathroom break, take a coffee break, stretch yourself. It's not a good idea to sit too long. And then at 7 p.m. sharp, we will resume the lecture. Okay. I will pause the recording for the next 6 minutes.
Sounds good. Thank you.
Are you guys back?
Yeah.
Yep.
Okay. Let's begin. It is recording, right? Yeah, it's recording. Okay. So, you guys already know linear algebra, but I will show you two things in one go. That is one, this library NumPy. Again, if you already know NumPy, it's fine. But more importantly, Google has built this very nice tool called as Colab. It's like your Jupyter notebook, but instead, it is hosted online, and it is free to use. For example, if you want to use, you just go to, you can simply go to colab.research.google.com, and initially, say you can do new notebook, and typically, initially, it might ask you to give permission to Google Drive so that you can store the notebook in Google Drive and other stuff. And now the first thing you have to do is you have to connect, right? So if you drop down, you can see, let's see, you can connect and it'll allocate, and you will get here. So you see you have connected to some machine, and you can get a GPU for free. You get some good RAM, other stuff, and now you can run stuff like this. Now here you can do NumPy as NP. and np dot zeros 3,4, and you can see you can run in NumPy, right? And actually, I think it also gives you GPU, but I don't know if this command works or not. Yeah, this is not the command to for this particular thing, but I can find some of the command that will you can run the code on the GPU. Let me see. I think the host run view resource, and if you want, you can also of course, if you already have some GPU or good CPUs in your own computer, you can connect to your local computer. And if you want, you can also connect to a custom Google Cloud instance. And now, if you want, I can get you a $300 Google Cloud voucher if you want to spend. And $300 will be plenty for you to do this course or other stuff. So just if you want, let me know, and I can get you that, because as a part of course they do give professors some leeway to give that money. But here I want to also show you how to use linear algebra in NumPy. More importantly, how to use this tool, and because this tool has a lot of stuff that could be useful in debugging. Because ultimately, it is not just that you are able to do something; you also want to show that to other stuff, right? Show the results to to other people. Especially for this project, you want to show it to other students, to me. So like any kind of notebook, it gives you two kind of boxes, right? There is either code box or there is a text box, right? So you can change. Sorry, what is this? Okay, yeah, this is like plus if you want to customize the editor and other stuff, you can do that. But you can also change whether it's a code box or whether it is I thought that is how I changed the code box. Yeah, see, because I have so many shortcuts in my system that I have to disable these shortcuts to enable. I'm trying to find if I can do
It looks like there's the insert code or insert text in the top left, right next to right above the word linear algebra.
Yeah, exactly. You can also do that. There's definitely, you can do this, but there's actually a shortcut. Like there's a command that automatically changes it to the code. What was that? Okay, never mind. So what we'll do is let me delete these things. So what is the benefit of adding a code? Adding a text is, this is your normal markdown. You can write stuff, you can add images, and you will see people have written like a whole tutorial course on Colab. And the reason I'm introducing this to you is because after the course, I will send you a nice GitHub repo where everything in the deep learning and all things that we'll do, people have written nice Colab, so you can simply follow through. And they might need GPUs, but because it is Colab, you can just connect and run. Let's connect here, and then I will disconnect this one because I don't want Google to disconnect and delete runtime. I'll disconnect that one. But in this case, like even if you leave something running, you don't have to pay anything. So therefore, there's no, like if you're running your own Google Cloud instance, you'll have to remember to close it, otherwise you are running through money, but otherwise not. And okay, so now that we know this, let's so let's see some of this stuff right here. Double click to enter. Okay, now you can run individual cells by clicking like this. Of course, it'll always tell you this for the first time, and you can see how much time it took to run. But each cell kind of runs so nicely that you can actually debug each individual cell. Now, again, I'm hoping you got, because I know two of you have not even used Python, so I'm guessing you are not familiar with NumPy. How about you, Tim? Have you used NumPy?
Yeah, I use NumPy a lot.
Okay, so for Tim, it might be boring, but for other people, NumPy is your one library in Python language that will allow you to deal with your scalars, your matrices, your vectors, and then do all the stuff. It's always a good idea to get familiar with NumPy, because once you learn NumPy, even the things that would not necessarily need NumPy, it is a lot efficient to do in NumPy, because the backend of NumPy is written in C++. So it is much faster than your standard Python code. So even though you are writing in Python, indirectly you are using very fast C++ code. And that is why people started using NumPy. But now NumPy is like very universal for machine learning, because machine learning is all about, handling your tensors. So that's, in Python, to import any libraries, you will, the one way is, people do this, import NumPy, and then now every time you will do NumPy dot, and then you'll write some function. But, NumPy has a long word that it is customary to import, give it a name. This is almost like your with clause in other languages, where, now NP is the name which refers to NumPy. Right, so here I say np.matrix, and then you literally give matrix, you define your own matrix. So now this is a matrix, and if you simply put A and run this cell, it it prints the matrix, right? And we also talked about transpose. Now the best part is we can see the best part is Colab. It has all this auto completion, everything built in, so you can actually, even if you don't know function, you can look at these functions and you can say, oh, what does this function do? You can do question mark and you will get a help here. You can see what does this function do? It returns specified diagonals. So say if I don't know if there's a function called transpose, I do transpose, and if I do a question mark enter, you can see here what the transpose does, what it returns. And for some of the functions, there might be shortcut also, like for transpose, this is T, because so often used. So you can see here, A.T is transpose of this, right? 540, 540. So there you have this. By the way, shift enter, runs the code, gets you the new line, alt enter, runs the code, doesn't go to the new line, something like that. Now let's make another matrix, right? And again here, values are put individually. You can also, sample the values from distribution. I'll show you how to do that. And now we have this. So now let's try to do some of these, simple linear algebra operations, right? So 5a, that is, so in this case, it's a scalar multiplication of a matrix, right? And it is as simple as doing this. Now, it might seem like very obvious, but you need to realize that behind the scenes, this asterisk has been overloaded, right? Because the language only defines this asterisk operation over two integers, or sorry, two numbers. But in this case, this is a number. You can see, you can do this type. So this is an integer, right? But if you do type of A, this is a matrix, right? So how is that an integer class and a matrix class object is multiplied? Because this operator has already been overloaded. And for NumPy, most of the operators will be overloaded like this, so you don't have to ever worry. There might be some operators, I'll show you, because some operators might have different meaning, most operators, their meaning is very intuitive and straightforward. So if you simply do 5 multiplied by A, now this is important to remember, is it will almost never change the original matrix unless you specify it, right? So in this case, this result is not stored anywhere. So if you think A has changed, it has not changed. If you want, you can do this. So now A will change to this, but more, maybe you want to store in a separate variable. So you can do C. And unlike other languages, this is dynamically typed, so you don't have to ever declare any variable before you use them. You simply give the name, and now you can see the type of C will also be a numpy.matrix, right? So if you do, C equals to A. Now, remember, this is the kind of thing, it's easy to fall into the trap, but I would encourage you not to do, because especially when you're comparing two objects, it is very, most of the time where if the code doesn't know how to compare them, it will compare the actual memory location. So are they the same object literally? Are they different references to the same object? In that case, it would say yes, others no. In this case, NumPy has gone ahead and overloaded where it is comparing. You can see it now. In this case, we didn't know how it will compare two matrices. It turns out it is doing element by element comparison. What would have happened if A were to be a different shape than C, right? How would it do that? To be honest, I also don't know. Okay, let's give this a try, right? Let's make another matrix called as np.1. So by the way, NumPy has all these nice functions like 1, 0. So if I give 2, 3, here I want to show you what D looks like. Right, so you can see here D is an array of 2 rows and 3 columns, all of ones, right? Now Let's see, Tim, you said you use NumPy. Guess what the output will be here?
I assume there's going to be an error.
Okay, let's find out. Right, so you can, so remember, there's no error, but there is output, right? I don't know, there's some deprecation warning is, there's some warning, right? But, if you were to put this output in some variable, right? Like this. Or if you were to use this, now the variable, the value of output is false, right? And in this case, is it okay? Is it false just because elements of D doesn't match this? How about if I had E, which is np dot once 3, 2? Now, if you see the sum of, by the way, the NP has also sum of E and sum of D are same, right? And probably other norms will also be around, will be very similar. But if I do D and E, you can see it is still false, because in these cases where there is no intuitive meaning, oftentimes the way it'll compare is actually it'll compare the actual the ID of the variable. So you can do something like this. You can look at the ID. So ID is like a memory location. It's not really memory location, but so because IDs are different, when you do equals to it is false. So if you are not sure, especially if you're new, I would encourage you to actually use function names rather than relying on these ordered operators, right? So, in this case, if you want to do, come on. So here you can see for matrix comparison, there is a function, and it is best to use a function like this, because that function will know to throw an error, right? If you give different, it'll tell you what happens if the shapes do not match, if x1 shape is not equal to x2, they must be broadcastable to a common shape. So now what does it mean to be broadcast? And there all this sort of stuff, right? So you can see here, it tells in description that behavior is different if they are different shape versus they are same shape, right? So that's why best to use actual function names like this. And in our office hours, I can run you through some of the useful NumPy functions. Okay, now
So
how about
a NumPy actually, in general, like we have a data set to load the data set. Once the data set is in our memory, then we work across each feature. Once the data is loaded and once the data is available in a variable, then we apply the NumPy operation and for every feature.
Yes, so basically what we're asking is, does NumPy operation apply to all feature of the stuff? NumPy operation applies to whatever NumPy object you give, right? So when I do, let's say np dot sum, right? Now, so this takes what? If you see here, it takes A is the first element, A is array-like, right? So it is an array-like, and typically NumPy, when it says array, it means a tensor. It can be any shape. Almost every, I would say 99% of NumPy operations are agnostic to the shape. So if your data is basically a spreadsheet, like a table, right? So then will the operation go through all the columns or each individual column? Depends on you, because you'll see most of the operations have this thing called as axis, right? This axis tells you how the operation will happen. Will it happen across all the axes, only at one axis? Here, let's try this, right? So we have this matrix B, right? If I do np.sum B, you see it gives me one single sum. What if I wanted a row-wise sum, right? If you wanted a row-wise sum, you will give axis equals 2, and now you will see here what it says. None or int or tuple of integers optional axis along which the sum is performed. So typically, axis goes from left to right. So first it is row. So if I do give 0, you can see here it will sum. Here, where is B? Let's look at the B. Where is? You can see here B. So now it is summing over all the rows, right? So this is 12 plus 5 plus 1 is 18, right? This is -2 plus 4 plus 5 is 7. But if you wanted a sum over column, then you will do 1. So now here you can see 14 minus 2 is 12, plus 12 is 24. So the answer to your question is, how does that operation happen? Almost always it's left to you. There's always a default behavior, but you have the choice to change it. And sometimes if you have, let's say, 3-dimensional, let's say 10 arrays, then you can sum over 2 different dimensions by basically saying, sum over 0 and 1 and leave the other one as it is. In this case, this is equivalent to summing over both axes because there's only 2 axes. Does that answer your question?
Yeah.
Oh, perfect.
I have another question, but I'll ask at
Sure.
the end of class.
Oh, no. Go ahead. Ask the question. So that
So,
is important.
Workbook and so does it mean that since I don't have the background of Python, R, it has a studio, R studio.
Yeah.
And R script, you can write in R script. So where you can write in 2 places. In the editor, you can write a script and you can execute. And R studio, you can write and execute using tool.
Yes.
So Python also might have some studio Python Anaconda. I think I have it in my local. I don't know what is it actually.
Yeah.
Okay. So the entire class for this course will be using this workbook or any other specific IDE to write the Python or like any other codes.
Yeah. So there's 2 things, right? Because I have used R, I know exactly what you're saying. So in R, what they have done is, so there is a script, so where you write, like it's almost like a text script, like a text editor. You write all the big script, and then you run the whole script as one thing, and then you have this REPL. REPL is like your interface, right? Where you write 1 line at a time. Here, both these things are combined. If I want, I can write the whole script here like this. I can write here, print hello a equals to np dot zeros. I think it's like this, 2,3, b equals to a multiplied by dot. I don't know the definition, so I will always check here. So just do the definition here. Let's see low, high. Let's see between 0 to 10. And now I can do print. So you can see here, this is not just for 1 line at a time. You can write your whole class, whole script here. And then if you want, you can actually just refer to this thing and run it. Oftentimes people, when they do write multi-line code, it is best to put them under some function. And this is how functions are defined. So now basically you have defined this function, and now you can run this function from wherever you want. Right?
I got it.
That way,
each line indicate. Okay.
Exactly.
Clear.
But yeah, so often, initially you will write 1 line at a time, but then if lines are very similar, you can basically do this, and I think you can merge by M. There is a command to merge. There is something to merge. I'm figuring out. Where's the toolbar? There was a toolbar. I don't see the toolbar. They keep changing stuff. There is a way to basically merge these different individual ones. They're here. Yeah, there you go. Merge selector cells. So now basically all this becomes in one thing, right? So you can do this. So as you can see here, plus, minus. Now, what happens if you do so this is where the matrix multiplication comes in. Initially, for matrix multiplication, I will encourage you to stick to np dot. So if you want to do dot product, stick to np dot dot. And if you want to do matrix multiplication, np dot mat mul. So don't use the overload operators because it's very easy to confuse yourself, right? If you're doing matrix multiplication, use this. If you are using dot product, use this. So you can do this, and now here there's more. You can see how now in the linear algebra, if you want to solve the set of equations, I could have guessed there is already a very good built-in linear algebra solver, and this has a lot of other stuff. You're going to see all the functions that np.lin LG has. You'll be able to see it has a lot of functions, right? To take the norms, to solve, to do SVD. I don't know if you guys learned about SVD and PC8 or our eigenvalues, Kolsky reduction, QR decomposition, everything is there. You might not need them all to write yourself, but it is possible that you might come across it. I might provide you with I might provide you some template that already has these things. You have to fill other parts, but the fact that if you see them, you'll recognize what they are, it's going to be useful.
I do have a quick question, so sorry to interrupt. to.
Go ahead. Go ahead.
To be honest with you, I'm kind of a little lost. I'm
Okay,
not sure.
no problem, no problem. So, I mean, definitely, if you don't know Python, this is definitely, none of this is going to make sense, right? My encouragement for you would be, take the next few days, just, refreshing up on Python. There are a lot of good resources. If you want, I will send you one website where you can interactively learn and try out exercises. I think Khan Academy also has that, because try to get slightly familiar with Python, and then try to see if you can, let me see if I can share my terminal. Let me see, share my terminal. So, I mean, right now, if all of this seems very, wait a second, what is going on? Wait one second. So if you have, Python installed, and then try to install something like IPython, just to pip install IPython. And it is best to start from here, where you can simply say import numpy as np, and then you try to write Python code in this interface where there are no distractions, right? Now
So I guess my only challenge is that I don't know where to start from. So like I said, if you have resources to send them to me.
Yes. Okay. So I will definitely send you. I will send you a very nice interactive way to learn Python, and try to do that. But again, remember, you might not need everything from the language, right? Our goal here is not to be expert in Python, but just to learn enough Python that you can execute these things.
Okay.
So, I will tell you what chapters there to do, but don't worry about doing everything there. But just enough where you feel that, oh, you like when you see these lines, it doesn't scare you, right? But as far as using this tool goes, the only way to get familiar with it is to just open this collaborativeresearch.goal.com and just try to play with it, right? Start from like a very empty one, and then start playing with this. And this play button just means run this line of code. So here, for example, here when I ran this line of code, you see here I get a very nice error. And the best part of this tool is, they have captured some of the errors. They give you more meaningful. They also allow you to search Stackflow, and often in the Stackflow you will find errors that always lead to some specific page. In this case, it's very simple, right? ANV is not defined. Why? Because ANV is defined here. I have not run that yet, right? So if I run this now, if I run this, you can see the code ran, right? So this is really good, useful tool to run Python code.
So at the end of every lecture, would you be providing us like a note or something just to go through, just something like
yeah, so that depends on what kind of lecture that we have, because I would say maybe it's like 50-50 or maybe 60-40, where there are some lectures which are going to be more background and theory heavy. There will be some lectures where there will be a lot of hands-on. So depending on the type of the lecture, I'll definitely take I will share with you Colab Notebook. This is where I was saying that the reason I'm introducing you to Colab is because there is a nice here Colab machine learning. This color is awesome. Something like this. Is this the one? Where is this? No. One second, let me stop sharing my screen. I have this very nice let me share my screen. So one thing you will find these days, right? So for example, here, there's this is a very nice, repository where, you have all this machine learning data science stuff, and everything is very nicely hands-on, where, if you go to notebooks, we can find all these different notebooks for, and, as you can see here, here, there's a lot of Python tutorial also. There's a lot of NumPy tutorial also. There's everything you need. So let's pick, something like introduction to NumPy, right? The one I'm trying to do. And so there's a new feature where if you see Python notebooks in any of the GitHub repository, you can directly click this link called as open in Colab. See, because you can simply sit here and just look at what is going on here, right? But it is best if you, okay, this one doesn't have much, but let's find another one where, let's say understanding data types in Python. Now you can click on this link and it will open a Colab, and now you can actually play with the data and you can run the code, right? So here you can now, if you want, you can basically, let's connect this. You're always remember to connect, although if you try to run first time, it'll ask you to connect. And now you can basically, run these things. And you can, for example, whenever you see play icon, you can play and you can see the results. So these are the kind of like the interactive textbooks these days available. And that is why I encourage Colab, because often you'll find these kind of resources, lurking around, and you can make use of them by, wait a second. Yeah, you can make use of them by just simply clicking on Colab and opening it yourself. So this one, Stefan, looks like it might actually it might actually serve your purpose, because you'll see it has a lot of introduction to NumPy, introduction to Python.
Right.
So why don't you start from this?
Yes, can you send me the link?
Yeah, okay, I'll send the link. Skip over pandas for now. Is really good for handling, tables and data sets, but you don't really have to. But then skip. Okay, you know what? I'll send you this link. Do chapter 1, chapter 2, skip chapter 3. Chapter 4 is useful for plotting. Chapter 5 is your basic machine learning, right? So, and I think chapter 6, we will, this is not chapter 6. So start with this. I do realize, okay, so I knew when I was writing this that there'll be too much stuff. So machine learning refresher, actually I had, this, slides again from another professor I had asked, where, it's very, these are these are like very basics of machine learning, but since most of you have already taken machine learning course, right? I will leave this for you guys to, look it over and, just get the gist of, what is, training set, what is a validation set, what's a loss function, right? These things. But next week when we meet, I will start with like very, very basic, like very limited, overview of some of the terminology in machine learning. But the fact that most of you have taken machine learning course, there's no point in me spending more time, telling you about these things, right? So next time when we meet, we will do whatever we are scheduled to do, but I'll start with a little bit of machine learning, but we'll start, diving into the building blocks of deep learning. But in the meantime, my recommendation is, if you already know Python, start with the textbook, read the chapters. If you don't know Python, really, get play with the Python, play with NumPy, because I think that will be the only thing that will, keep you from keeping up with the pace of the class. And it is best to do it now compared to later on when you will have more stuff to learn. Does that sound okay with you guys?
Yeah, so you can send me the link.
Yes, I will send you the link on Slack. Yeah.
Please include me, Professor. Include me also in that email.
Okay, no, I will send it on Slack on the general channel so that all of you can see. And as soon as the videos are saved to my disk, I'll upload the videos. But I'm really looking forward to the class, and I'm always available on Slack and also on email. If you have any questions, please don't hesitate. But like instead of directly asking in DM, I'll encourage you to ask in the general channel, because oftentimes same people might have same issues. So even though I'm answering you, other people might also learn from that. But for some reason, if you want to ask me individually, that's fine too.
So are we going to get that material?